Okay, so thank you very much. So I'm talking about the quantum version of a problem that in its classical version was very much at the beginning of statistical physics, namely the question of irreversibility in isolated systems. So this question of irreversibility arose in this famous debate between Boltzmann and Loschmidt, which is essentially about the question, how do you reconcile the second law of thermodynamics, or the observed error of time, with the fact that on a microscopic level we have time reversal invariance. So we ignore CP violation. And so Boltzmann derived, using his Boltzmann equation under certain assumptions for gases, the fact that the entropy of an isolated system is a non-decreasing function of time, and consider this an analytical proof of the second law. Loschmidt famously objected to this with the following Gedanken experiment. So imagine you have a gas that is confined to part of a volume initially, then you remove the separation and the gas is going to expand into the whole volume. So the entropy is going to increase, as the second law tells us. But then if at a certain point in time you decide to invert all the velocities of your gas molecules, then because the microscopic laws of nature are time reversal invariant, you must run back to your initial state. So then the entropy must decrease again. So essentially, this is the question: dear Boltzmann, how can you derive something like this from equations of motion that are time reversal invariant? The answer to this objection attributed to Boltzmann is very insightful. Then try to do it. This is a very good answer, and has been elaborated on a bit more by Thomson, whom you probably better know as Lord Kelvin. And he makes the following observation. So yes, we go back to this Gedanken experiment with the gas expanding into the full volume. If you reverse the velocity, the motions of all the molecules, yes, you go back in time. But if you don't do this with increasing accuracy, as basically the time that you let the system initially evolve become longer, then any deviation from absolute precision will make it impossible to go back to your initial state. So I dug up this numerical simulation of the situation. So here you have some particles, in 2 dimensions, sitting on these lattice points. They all have the same magnitude of velocities, but in random directions. And then the authors let this system run, and you see it becomes kind of the configuration looks random. What's plotted here is h, so that's minus the entropy. The entropy increases as it should. And then the question is, if you do this time reversal operation, do you go back to your initial state where the entropy becomes smaller again, or do you not? And here are some of the data points. So let's start with this fully drawn out line. This is bit molecular dynamics, which basically means integer arithmetics without any errors. And you see these times TA, TB, DC, DD. That's basically where you do the time reversal operation. And you see you always end up with your initial state, because you're not doing any rounding errors, so you must get back. Then they use floating point molecular dynamics. I think that was single precision floating point. And you see that for a short time, TA, you go back. But for the larger time, TD, you stay down here. So you don't go back to your initial state anymore. And then they do, again, this integer arithmetics calculation. But then at this time, before they reverse all the velocities, they have the butterfly interact with the system, so they shift a few particles. And again, you can see that for the longer time, you do not go back to your initial state. So this is kind of, in a simulation, a modern simulation, what Thomson was saying here. So the question of irreversibility in this picture is not the question whether you can go back to your initial state in theory, but whether you can go back to it in practice. So if it becomes too difficult to run the evolution backwards in time, then you call this irreversible. In modern language, one is dealing with a classically chaotic system which has positive Lyapunov exponents. Therefore, the time reversal operation requires an exponentially increasing accuracy with the waiting time if you want to hold your if you want to go back to within a given vicinity of your initial state. And this is what one can define to be irreversible dynamics. So it's a question of not what you can do in theory, but what you can do in practice. And if the accuracy required grows exponentially with this time t a, t b, t c, t d, then you call the dynamics irreversible. So here again, if the forward time evolution, then we have some small perturbation. We run back, and if this thing grows exponentially, then we have a positive Lyapunov exponent. So this is the classical setting. And before we move to the quantum system, one observation: this Lyapunov exponent that governs this divergence of trajectories, this is determined by the unperturbed system. This will become important in the quantum setting. So this is an intrinsic property of the system that drives the time evolution. It's not a property of the perturbation, which makes perturbation theory later very difficult or impossible. Okay, so the goal is, we'd like to understand irreversibility, but now for isolated quantum many-body systems. Okay, so obviously people have thought about this question before, and one quantity that has been looked at a lot is the Low-Schmidt echo, basically suggested by Asher Perez in 1984. And his idea is the following. So you take some initial quantum state, you forward time evolve it with a Hamiltonian, and then you do the backward time evolution where you add some small perturbation, sigma, to your Hamiltonian, and then you look at the overlap with the initial state. And if this thing decays quickly, in some sense, then you want to call this dynamics irreversible. So a lot of work has been done on this quantity, and I'm not planning to go into this because this definition of irreversibility is useful, very useful for a few body systems, but it is not a useful definition of irreversibility for quantum many-body systems. So this is a point that I like to make. The definition is not right or wrong. A definition is useful or not useful. And I want to explain why this is not a useful definition for quantum many-body systems. And this is based on an insight that we have learned in non-equilibrium quantum many-body systems, which is unfortunately called the eigenstate normalization hypothesis. I mean, it's not so much a hypothesis anymore. It's actually been at least numerically seen in many systems. And this is the following observation. So we are looking at a non-integrable quantum many-body system. And we are looking at many-body eigenstates that are far away from the edge of the spectrum. So we are not making any statements about physics close to the ground state. And now if we are looking at few body observables, so operators that you can express in a few fundamental fields, then these few body observables cannot distinguish nearby many-body eigenstates. In the sense that if you take two nearby many-body eigenstates, so they're separated by a certain number of many-body level spacings, and evaluate this few body observable, the expectation value, then the difference of the expectation values is suppressed by something like 1 over the dimension of the Hilbert space. So it becomes effectively impossible to see this difference. So this means that a single eigenstate is typical in a small energy interval. Take two many-body eigenstates that belong to different energies, so they are, of course, orthogonal, but there is no observable, no few body observable that you can write down that can actually distinguish them. So from this point of view, the orthogonality of states is not a useful criterion for calling them physically different if you cannot come up with a measurement, a very realistic measurement that can distinguish them. And that's the basis of my statement that I think the Low-Schmidt echo is not a useful quantity for characterizing irreversibility in quantum many-body systems. So the definition of irreversibility that we've been using is very much modeled after what experimentalists actually do when they study kind of forward-backward time evolution, let's say in spin echo experiments, and that is we look at echo dynamics. So we look at some observable, think of some magnetization that under time evolution decays very rapidly, and then at some waiting time tau, we do our time reversal with some small perturbation, and then this starts running backwards, and we will observe some echo peak that will typically be smaller than the initial value. So what we are interested in now is how does this echo peak basically divided by the initial value of the observable, how does this decay as a function of this waiting time tau for a given strength of the perturbation? Sometimes one needs to take into account that this observable has a non-zero expectation value for long times. So you want to look at the contrast and subtract the contrast. And then if you really do the calculations or the numerics, you can see that these echo peaks can be really, really sharp. So, and their peak can be slightly shifted from 2 tau, which one can understand. So you actually need to look at the vicinity of this time 2 tau and find the maximum. This is all things that we didn't know initially and produced results that didn't make a lot of sense. So anyway, after paying our dues, this is the quantity that we looked at, the normalized echo peak height, and we are asking the question, how does this thing decay as a function of tau? And what we define as irreversible dynamics is that this object decays exponentially or faster as a function of the waiting time. Otherwise, we call the dynamics reversible. And the perturbation strength only enters as a prefactor. It doesn't affect the rate with which this thing decays. Okay, so this is our definition of irreversibility. And so my goals for this talk is I'm going to show you a kind of a collection of various results based on this definition for one integrable and two non-integrable quantum many-body systems. So I'm not going to go into very much into the details of how we were doing this, but I'm mainly showing you the results. Okay, so the first model that we looked at, so this was in collaboration with Markus Schmidt, a former PhD student of mine. We looked at the kind of very popular model in non-equilibrium quantum many-body systems. That's the transverse field Ising model. That's Ising interaction plus some transverse magnetic field. This is an interesting model for many reasons. It has a quantum phase transition. And what makes it very attractive is it's integrable. And it's integrable in a very simple way. It becomes quadratic in fermions after your Wigner transformation. So you can calculate many, many things analytically. Although it is so simple, it does show thermalization in a certain sense. Namely, if you prepare the system in a ground state with some transverse field, but then drive the time evolution with a different transverse magnetic field, and you look at some finite region of spins, and look at the kind of the reduced density matrix in this region, then one can show, as done by Fagotti and Essler, that in a sense that this converges to something which very much looks like a thermal density matrix, except that one needs to take into account additional conserved quantities because this system has so many conserved quantities. So this is what's called a generalized Gibbs ensemble. So although this system is so simple, in a certain way, if you look in real space, it becomes thermal plus these additional conserved quantities. Okay, so what we were interested in are now basically studying this kind of echo behavior. So we always prepared the system in the ground state with some transverse magnetic field. Then we did the former time evolution with a different transverse magnetic field, which typically means that observables decay very quickly. And then we do the backward time evolution, and we played with a number of different protocols. So for example, this is very much a suggestion by Paris. So we just do the backward time evolution. So here we have a plus instead of the minus, but now we change the magnetic field slightly. Or we do a transformation, a unitary transformation that is very similar to this kind of velocity reversal transformation that Loschmidt suggested. Or we do something like a generalized Hahn echo where we change the sign of this magnetic field. The observables that we looked at are the transverse magnetization and the longitudinal spin-spin correlation function. And this, because this model is so straightforward, one can basically boil everything down to some numerical evaluation of determinants. And you can take thermodynamic limit, which gives you very accurate results. And you can also get analytical results for large waiting times based on some stationary phase approximation. And so this is how this typically looks like for this kind of quench, the backward time evolution with a slightly different transverse field. You see the magnetization initially decays, the transverse decays very quickly. And then at this time, we do the velocity, we do the time reversal with the slightly shifted magnetic field. And then here around the time 2 tau, we observe the echo peak. So for a larger time, you see the echo peak here. And what we are basically asking is, how does this thing now decay as a function of the waiting time tau? So here are some typical results. And with pretty much all the protocols that we looked at, and for the observables that we looked at, we find essentially the same behavior, namely that these echo peaks decay algebraically with exponent -1/2. So this is for the transverse magnetization. These fully drawn out lines are based on the analytical prediction. One can, for some observables, one can even work out the prefactors, and one can see that the prefactor of this algebraic decay law, that depends on the strength of the perturbation, but the exponent is always the same. And down here, that's for the spin-spin correlation function for various distances. And again, if one waits long enough, especially for large distances, one always finds this algebraic decay law. Then we also looked at the entanglement entropy. So this is, we are looking at the reduced density matrix of some subsystem and calculate the von Neumann entropy. And now it is known that for such non-equilibrium time evolution after a quench, the entanglement entropy grows linearly with time. This is what you see here. And then at this time tau equals 30, we run the evolution backward in time. And if we don't do any perturbation, of course, we do come back. This is this green line, back to the initial value as it should. So here the entanglement entropy really becomes smaller as a function of time. It's actually not 0, but it's just very small. But if you have again some perturbation on the backward trajectory, you see that you don't go back all the way. And you can again study how this scales with the waiting time. And again, you find this algebraic decay tau to the -1/2, also in the entanglement entropy. Okay, so this is so based on this, based on our definition for this very simple model, with respect to the observables and this kind of non-equilibrium dynamics that we looked at, we would call this reversible dynamics. So the obvious question is, what happens if you look at something which is non-integral? And so this is again work done with Markus Schmidt. So we looked at some non-integrable XY models. Did 2 versions. One that was fully connected, so where all spins talk to one another, but with matrix elements that were drawn randomly. And then we also did a local model where we had nearest neighbor and next to nearest neighbor interactions to make the model non-integrable. We tried a number of different numerical methods. So for example, initially we thought TDMRG might be a very good method, but unfortunately entanglement growth in between still kills you. So in the end, it turned out exact diagonalization was the best method, because at least we didn't introduce additional errors because of truncations. The time evolution is always we're starting from some Néel state, and the way we introduced the perturbation here was that we act on this state after this waiting time t with a Hamiltonian with somehow different spin interaction for a short time delta t. So we have the system evolve unitarily with a different Hamiltonian for a short time. And then after that, we run the evolution backwards with the initial Hamiltonian. And then we basically ask the question, what is the echo at 2 times the waiting time? Okay, so and now these are the collection of results for the staggered magnetization. This is a spin structure factor, so that's a spin-spin correlation function, and here's again the entanglement entropy. Up here, this is data for the local Hamiltonian, for this local Hamiltonian with 24 spins. Down here for this fully connected one with 22 spins. So there's many more matrix elements. And these different traces that one sees here, that is different times delta t for which this random perturbation acts. So if delta t is large, you have a large perturbation. As delta t becomes small, you have a weaker perturbation. So first of all, this is numerically really hard. You're looking for a small echo peak on a noisy background. Yeah. So at some point, you really cannot say anymore what your echo peak is. So I'm showing you the full data, but for example, stuff like this down here, this is in our interpretation, this is just noise. So you cannot basically you cannot trust the data all the way down here. It's impossible to extract the signals. And then each single data point in these curves is quite a bit of work because it comes from running the evolution forward, perturbing, running it backward, and then finding the maximum. So there's quite a bit of work that Markus put into getting this data together. And now what you can see is that for the observables that we looked at here, there is a time window where this looks reasonably well like an exponential decay. And what you can also see is that this rate here becomes pretty much independent of the strength of the perturbation. I mean, it varies by a factor of 10 as you go in this direction. It's especially nice in this fully connected system down here. So our conclusion was that this is a kind of a numerical indication of an exponential echo decay with a rate that is indeed independent of the strength of the perturbation. Of course, one does suffer from the fact that the systems, are not extremely large. Because of that, we also looked at another non-integrable model. So this is a collaboration with some of Anatoly's people. Tris was also involved in this. So we looked at the Sashdev-Yekitayev model, which is the version that we write down here is we have fermions that only interact with one another with a random 2-particle interaction. This is a really a beautiful model. It is non-integrable in the sense of level statistics, but it becomes exactly solvable in a way that one can make precise in this large n limit. It is maximally chaotic in the sense of saturating a certain bound for the Lyapunov exponents. It has some approximate infrared conformal symmetry, which indicates that there might be some holographic dual. So this is a really fascinating model to work with. And it was interesting for us because we could use an approximation, this truncated Wigner approximation, that Anatoly Polkovnikov has worked on a lot, which allows us to get results in the thermodynamic limit, and which we believe becomes exact in the limit large n where the system becomes very large. We cannot prove this, but the numerical tests that we did seems to indicate that. Our initial state is such that we have a certain fraction of these states occupied, and then we basically look at the expansion of this occupied, of these fermions into the whole system. So it's very much this, this Low-Schmidt-Gedanken-experiment. And the observable that we look at is the occupation imbalance. So how much of the occupation imbalance, no problem, do you get back at the initial time? If you act again with a perturbation, which is a random hopping Hamiltonian that acts for a short time, delta t, and what you vary is this time delta t where this random hopping Hamiltonian acts. So what, for historical reasons, what we actually did here is we looked at how this echo peak basically behaves for actually short waiting times, so how it starts deviating from its initial value. So we looked at the initial decay of this. And what one finds is an exponential decay, which is what one sees here is shown as a deviation, so as a function of the waiting time for different strengths of the perturbation. So this is a large strength of the perturbation, and here the perturbation becomes weaker. And one can see that it very nicely approaches a line, which means one has an exponential decay. And here one can actually understand the slope of this line that's consistent with the classical Lyapunov exponent if one takes the classical limit of this system. So again, in this system, one finds an exponential decay of this echo observable that we looked at. OK, so this brings me to the conclusions. So we suggested a definition of irreversibility based on the decay of echoes in observables. For the one non-interacting, very simply integrable model that we looked at, the transverse field Ising model, for the things that we looked at, we always found this algebraic decay of the echoes, which is what we would call a reversible dynamics. For the non-integrable models that we looked at, we always found an exponential decay of these echoes with a rate that looked independent of the strength of the perturbation as far as we can see. And so the to-do list is obviously, I mean, look at other more interesting integrable models and other non-integrable models to see whether this picture that I would like to deduce from this is indeed holds more generally, apart from these models that we looked at. There's a number of interesting connections that one can make. People have recently been very interested in out-of-time order correlators, and one can actually see that there's a connection of these out-of-time order correlators with echoes. There's a connection to scrambling physics. You can ask, why are there actually echoes in the first place if the state that you forward and backward time evolve is orthogonal to the initial state? And one thing you would really like to understand is what actually determines the rate of this exponential echo decay. And the quantity that you would like to do the perturbation theory in, that's this the small butterfly perturbation. That's not a good perturbation theory to do, because if you do that, you end up with a rate that depends on the strength of the perturbation, which is exactly what you don't find. So that's why it's not clear to me how one can access this analytically, at least for general problems. OK, and that's it. Thank you.